Oh my, the recording accidentally stopped automatically. So I need to record again. Okay, bear with me. Let me check. Where do we stop? Okay. Okay, the time dependent Schrodinger equation. This is step one. As I mentioned before, we don't need to learn the derivations one by one. We just need to know why do we need to do this, which I have told you just now, right? So then we go to the second step of time dependent Schrodinger equations. So this second part completes the idea of combining the kinetic energy term and potential energy term. Remember, electron is moving, it has kinetic energy, and the electron has correlation energy with the proton inside the atom, and there it will rise the potential energy. So we have the kinetic energy from moving electron and potential energy with the correlation of the charge, negative charge with the positive charge, and also with the neighboring positive and negative charge. So we combine the kinetic energy term and potential energy term into one equation that governs time evolution. We want to know what will happen to that subatomic particle by the next second. You want to see how the wave function evolves, right? So again, I do not want you to memorize the steps. So many steps over here, as you can see. So many steps, okay, from the first, second, so on and so forth. Okay, boleh tengok dekat bawah nanti lagi. We can scroll down. Okay, we scroll down. See? So I want you to understand the reason why we do these derivations. We are showing that the particle in quantum mechanics evolves according to its total energy. Just like in classical physics, but now the object evolving is the wave function. In classical physics, a particle is a particle. It doesn't move like a wave function. Okay, we cannot predict the movement. We cannot see actually the movement. So we need to treat them as wave-like, right? So the final equation becomes a compact statement of a very powerful idea. If you know the energy landscape, you can predict how the quantum state changes with time. All right. So in density functional theory, we call this as TDDFT, time-dependent density functional theory, which we could predict the electrical properties of any materials at any time. For example, if we try to heat up a semiconductor, what will happen? If we try to expose a semiconducting material under the sunlight with certain energy, we could predict what will happen to the energy levels and to the electrical properties of the material. So why do we need to trouble ourselves of predicting properties of materials? That's the main question before we come into the solid state physics. Why do we need solid state physics? Why we are talking about so many simulations, calculations here and there? Why don't we just go to the laboratory and start to do our lab work, the physical lab work? So it's going to be like this, yeah? Because materials are not cheap. Chemicals are not cheap. Semiconducting materials are not cheap. So we don't have the luxury of wasting our chemicals in the laboratory. Laboratory is trying to explore things. It's a place where we try to explore things. The term explorations mean we must bear in mind that we will waste certain parameters. For example, we will waste time, we will waste our resources because we are trying to do trial and error. Right? We do calculations for simple calculation. Okay, before we need to mix this 1 mole with this 1 mole, then we will get something 1 mole. But sometimes the calculations went wrong. So we will waste lots of chemicals. So why don't we try to simulate first to see whether the chemical reactions could happen and could turn out very successfully before coming into the laboratory. So we have 30 sets of virtual experiments, and we only pick one experiment that could possibly go success. And then we go to the laboratory and do our physical experiment. So that is the motivation. Why do we need the quantum chemical calculations? Right. So look at the next slide. Oh yeah. What does it mean by the time-dependent Schrodinger equations? The physical meaning of time-dependent Schrodinger equations. Okay, you could play around with we have this simulation on your left-hand side, which we could animate and play around with later. But let me explain something to you first. So this is where the equation starts to feel physical instead of abstract. Right? On this slide, focus on the simulation on your left-hand side. Look at the simulation. You can animate the wave function, look at its curvature, and compare that with the potential. Right? So what I want you to notice is that the wave is not bending randomly. The curvature tells us something about the kinetic energy contribution in the equation. When the curvature changes, the kinetic term changes as well. You can start playing around with the sliders, right? So this simulation helps us connect the mathematics to a picture. The wave function shows the states. The curve shows how sharply the state is changing in space. And the potential shows the environment acting on the particle. So when you play the animation or change the quantum number, you should ask yourself how the shape changes, where the curvature becomes larger, and what that means physically. So let us try to play around with the quantum number, starting from quantum number equals to 1. So we go quantum number equals to 2. Yeah, now look at the wave function. So from group 5 explanation last week, if we change the quantum number, the n, look at the nodes. What happened to the nodes? So if n is equals to 3, the nodes will become 3 minus 1. So the nodes will be 2. That's why we are looking at 2 nodes over here. Right? Now look at the wave function, how the wave function changes. So quantum number equals to 3, the nodes becomes like that. Quantum number equals to 4. Oh, we need 5. Where is 4? 4. The nodes become 3. And the wave function, becomes something else. Look at the curvature. What is the meaning of the curvature? The curvature also changes. See? Look again. This is the wave function of n equals to 1. The curvature is just like that. Okay? The curvature. We want to see the curvature, how curved it is. It is less curved. That's why your curvature looks like a flat line. Now, quantum number equals to 2. Now the curvature, so the wave function looks like that because we have one node. So the curvature is like that, it's sinusoidal, and the curvature becomes even more curvy. And how about n equals to 3? See, it's even curvier, if that is a word. The nodes becomes 2. How about 4? The nodes become 3. Then the curvature becomes even more and more curvier. And if you click on increasing, you could see that, oh, saya sampai 5 saja. 5. Becomes more and more curvier. So again, what does this mean? What does the curve means? Find out. Find out. If we change the quantum number from n equals to 1, 2, 3, 4, and 5, or even more, the curvature becomes larger and larger and larger. It's the wave function becomes more curvy and curvy and curvy. And I need to ask you, what does this mean? You need to find out now which group. I think this will be question for group 1. I think so. So group 1, Be prepared. What does it mean by curvature? The clue is over there. I have mentioned the clue. Saya dah terbagi clue. See. Sharp bands, high curvature means high kinetic energy. Because why high kinetic energy, sir? Why high kinetic energy? So, class, what does it mean by the quantum number? N equals to 1 is actually the ground state. It's when your atom, your material hasn't absorbed any energy from the sunlight. So it is in the ground state. For example, the material in the dark room, you don't absorb any energy from the sunlight. So the energy very, very low. So N equals to 1. N equals to 1, you have no node, and your curvature is quite flat. So it means your electron doesn't have any high kinetic energy. Only the kinetic energy in the dark. So what happens if the electrons start to absorb energy from the sunlight? N equals to 2. It means that your electron has excited into the first excited state. First excited, it absorbs energy, but not that much, and the electron has excited to the first excited state. And therefore, your curvature, you have one node over there, and you have a curvature of sinusoidal graph, which higher than that of the N1. It means that your electron already absorbed higher energy, has higher energy. And same goes, if you keep on absorbing light with higher energy, your curve becomes even curvier. It means that your electron now has much higher kinetic energy. Kan? Tu Pak. Nampak curve ni semakin tajam, atau semakin curvy, it means that your electron is in a state where it carries very high kinetic energy. Just like that. Right? Sorry for the noise outside from my room. My kids, kids, it's 5:20 p.m. They are playing around. They have high kinetic energy. They need to express themselves because two of them, they are autistic, just like their father. I think I'm a undiagnosed autistic person. I think because two of my children, they are ADHD and autistic. So it's in the DNA. So I haven't checked myself. Yeah, people call me sometimes weird, have this peculiar behavior. So most probably I have this trait, some maybe in the spectrum of ADHD or autistic. Anyway, so this lecture is not about me. Let us take a look at the next slide. Now, why do we need to learn this? Why do we need the time-dependent Schrodinger equations? Why do we need to learn the density functional theory and all that? So in the application, without the quantum mechanics, without the solid state physics, we won't have these two most important instrument for material scientists, which is the STM, the scanning tunneling microscopy, and also the transmission electron microscope, which they really help us during the laboratory section. Now, let us connect the theory to a real instrument. The scanning tunneling microscopy, or the STM, works because of quantum tunneling. Quantum tunneling, we haven't discussed this yet, but it comes after the time-dependent Schrodinger equation. So classically, if an electron does not have enough energy to cross a barrier, let's say the electron is traveling, but we have a barrier in front, and it doesn't have enough energy to cross the barrier. The barrier could be infinitesimally very high, and this electron could not pass through. Remember, electron is a wave function, can be described as a wave function, because if it could not pass through, what can you do now? So if an electron does not have enough energy to cross the barrier, it should stay on one side, this side only, because you cannot cross to that side. Okay, but in quantum mechanical, the wave function can extend into and through the barrier. The one that we're discussing just now is in terms of classical physics. if this electron does not have enough energy to cross a barrier, it will stay at this side. But in quantum mechanics, the wave function, this electron is a wave function, can extend and through the barrier, giving a small but measurable probability crossing the barrier. It is nearly zero, but not zero. So if it's not zero, we could get some information from the other side of the barrier. So the scanning tunneling microscope uses exactly this effect, the tunneling effect. Okay, I believe I mentioned this to group 5 last week, group 5, kalau tak silap kan, about the tunneling. So macam mana dia buat? How STM works? So a tiny tunneling current flows between the tip. Okay, look at the picture, the tip and the sample. The tip provides us the electron flow from the STM. The sample is our barrier. Okay, the current from the tip try to go through the sample, but it cannot because the barrier is very big. But somehow in quantum mechanics, the electron is a wave function, and somehow the wave could penetrate through the barrier, even though the current is extremely small. And remember that the current is extremely sensitive to distance. So this is why STM can map surfaces at atomic scale by nearly to touch the sample, and the space between the tip and the sample could be in a scale of angstrom. So with that very small gap, the electron could pass through the barrier and giving us some information about the surface of the sample. So this is one of the clearest examples of why Schrodinger equation matters in real technology. So later we will have this calculation. Look at the tunneling current equation. This is superbly important. I did mention that the current from the tip is very sensitive to the space between the tip and also the barrier or the sample. This is the sample or the barrier. So this is our tip, the tip from the STM, the probe or the tip, and at the edge, at the edge of the tip, we release electron flow to try to enter the barrier or the samples. So the electron flow could be denoted as current. The current is very sensitive to the distance between the tip and sample, so it is current proportional to the exponential of negative 2 kd, where k is, sorry, not k, kappa, exponential of negative 2 kappa d, and kappa can be calculated from this equation. Square root of 2m phi minus energy divided by h bar. If certain value is given, so you could calculate the kappa, and if d is given, you could calculate the current. So remember, these two equations are superbly important. Later we'll try to solve certain problems using this equation, and the equation will be given during the test. Remember, right? Now, all right. So this is an interactive simulation of quantum tunneling. The one from your left-hand side. Okay, for example, left-hand side. This is a wave function. The electron try to penetrate the sample or the barrier. The barrier is the red barrier. Okay, so it moves towards the barrier. So what will happen? The tunneling could happen depending on your particle energy. Right. So let us look at, this is slide number 20, I think. Okay. This simulation here to help you to see the tunneling instead of only reading or hearing about it. So on your left-hand side, you could see the wave approaching the barrier and interacting with it. Okay. And then either being reflected or transmitted through. All right. So on the right, you can adjust the particle energy, the E. You can play around with the slider. So the barrier height, V naught, V kosong tu, V naught, the barrier with A, and the packet spread sigma. The barrier width denotes as A, okay? And the packet spread denotes as sigma. So start with the energy lower than the barrier height. Let's start energy with lower than the barrier height. Energy. We want to play around with the energy first. Kita adjust the energy lower than the barrier. Barrier tinggi sikit ni kan, tinggi ni. Kita cuba adjust the wave function with energy lower than that. Kita try ya. So saya bagi yang lagi rendah lah. Lagi rendah. See? Saya restart. Ataupun barrier ni saya letak tinggi lagi. Baru best. Datang. See? Certain of the wave could be tunneled through the barrier. And that tunneling effect will give us some information that our detector from STM could detect and translate into images. The images of what? The images of the surface of our samples. This is how the scanning tunneling electron microscope works. Okay. Hantam dan tunneling effect happens. So this wave very important because it carries information. Same goes for this wave. The reflected, this one is reflected wave. This is one, the tunnel wave. The reflected and tunnel wave, they carry information that we could use to develop image. We could process the image of the unseen things, nanoscopic, angstromscopic scale. So what else we could play around? So you have seen just now that the wave does not simply stop. Instead, it decays a little bit or much more. It decays inside the barrier and a smaller part appears on the far right-hand side. Again, if you see the amplitude of the initial wave, when it hits the barrier, it decays and small part with smaller amplitude penetrate the barrier. So the transmitted wave, the reflected wave, both can be used to develop or to regenerate images of the unseen things. So that is tunneling. Now let's try to increase the energy until it becomes greater than the barrier height. Let's try to increase the energy, or we could make the barrier height even smaller and we try to increase the energy. See, yes. If the energy of our electron beam is much higher than the barrier, what happened? What happened here? Okay. So you could see that much more wave could transmitted through the barrier. And much more. So much more information can be given to us to generate the images. We could play around. So this, sometimes if you later, when you are doing FYP2, maybe you need to check to observe your sample using the STM, the FISM, the electron microscope, sometimes the operator of the electron microscope will use the lowest energy of the electron so that we don't want to waste electricity kan. Electricity sekarang mahal. Nanti akan ada tax untuk electricity naik tarif lagi kan. Okay, right? So he uses the smallest energy of the electron beam first. So if the image is not clear, he keep on increasing the energy of the electron beam until the image is sharp enough. So what he's doing is that trying to overcome the barrier or to overcome your sample. Please remember this. Later you will understand when you do the FYP2 if you are using the FISM, right? So also we could play around with the barrier kan. Barrier semakin besar, what will happen? See. Atau mungkin kita kurangkan sikit energy, kurangkan sikit. What will happen to the energy? Let's say the energy is at par with the barrier, what will happen? Oh, it transmitted through. Tak ada kesian-kesian, transmitted through macam tu saja. We can play around kan. Try lah. So this one energy is much lower. Much lower. Yeah, see. If the energy is high enough until yang warna kuning ni kan, the yellow part is actually the energy level of the electron beam. So this one, the energy level of the coming electron beam is lower than the barrier. So if we overcome the barrier, it means that our wave can transmit through very easily. Atau kalau lagi tinggi, kan, transmitted through very easily. But more can be transmitted through. Right. So you could also play around with the packet spread if you want to. Maksudnya packet tu lebih besar kan, packet of energy. See, this is real simulation. Bukan artistic artist representation. This is real. As you can see, my video also lags right now because my computer is simulating something for you. It lags a bit. Okay, so next, what else? Okay, now we have discussed the time-dependent density functional theory. Of course, we have the other part of the world, which is time-independent time-independent Schrodinger equation. So far we have focused on change with time, the TDSE, right? Now we move to a special but very useful case, the TISE, the time-independent Schrodinger equation. This appears when the potential does not change with time. The potential energy, the U, the interaction between the electron and neighboring electron, and also the proton inside the atom, right? So this appears, the TISE appears when the potential does not change with time, which is common in many physical systems actually. In this case, we can separate the problem into spatial part, bukan spatial, tapi spatial part, which means the part of the equation which discusses about space, ruang. So in TISE, we separate the equations into spatial part and time part. This is extremely important because it allows us to solve bound state problems and find allowed energy levels. We use TISE to find out the energy level of these electrons. Yes, energy level, whether it is ground state or first excited state, second, third, fourth, and fifth, also the ionization energy level. So in practice, this is why quantum mechanics becomes especially useful for atoms and many solid state models. For semiconducting materials, this is very important because we need to know the ground state and also the excited state, because before we fabricating any devices, we need to have this knowledge. Why? Because ground state electron cannot be moved, cannot be mobile. Only the excited state electron can initiate electricity. We know electricity comes from the word electric current. Electric currents mean movement of electrons. And which electron can be moved? Only excited state electron, not the ground state electron. The electron that is bound in the atom cannot be moved. We cannot create electricity from that. We only can initiate electricity if the electron in the atom is being excited at n equals to 2, 3, 4, 5, or even more. That's why TIC is very important for us. Okay, now we look at the next slide, the separation variables and procedure. Again, the key idea on this slide is separation and variables. We assume we don't want you to do the derivation. This slide is just to show you the derivation which the previous scientists have done before. Kenapa dia tak? Ayolah, okay, nampak dah. Alright, so saya punya slide lag sedikit. We assume that the full wave function can be written as a product of space-dependent part and a time-dependent part. Remember, TIC, we have space-dependent, time-dependent part. This may look like a mathematical trick, but it is actually a very powerful physical simplification. Remember, I don't ask you to memorize this. The computer will do this. We just need to understand why derivation is like that. So it tells us that for system with a fixed potential, meaning that if we don't change the position of the electron and proton, right? So the potential between them is fixed. So the spatial shape of the state can be studied independently from the time factor. So once we do that, the problem becomes much easier to solve. Remember, our psi now, our Schrodinger equation now can be separated into space-dependent and a time-dependent part. Now, I have to open my door for my daughter. Okay, you can enter, but please be very quiet. Silent, please. I'm giving a lecture. Where am I? Where were we just now? Over there. Don't interrupt. Apa tadi? Interruptions make me forgetful. I can't remember. Okay, now the wave function, we can separate them into the space part and also the time dependent part. So if we fix the potential part, therefore this the spatial shape of the state can be studied independently from time factor. So the main things to remember is that separation helps us find stationary states, and those stationary states are the building blocks for many quantum systems. Later, I know, but it is very hard for you to imagine right now, but please keep the notes and also the claw notification. Please keep the notes and the video. Later, we will try to use the simulation tools we have. You can install the simulation tool. We try to generate images of the location of electron at certain part of the structure. Now, please do not disturb me. You want the air condition, right? Just sit over there. We have air condition over there. Do not interrupt, right? But do not interrupt and do not make any noise. I'm recording my lecture. Please do not make any noise. I just told you 1 second ago. Sorry, I have to speak in English. Mana tadi? Yeah, slide 24. This slide 24. This one. Nah, please do not disturb, or else I ask you to go out from my room. Sikit je lagi. Alright, now we have arrived at the time-dependent Schrodinger equation itself. So this is the TIC. Don't ask me how we could derive the equation until this point. We don't learn the derivation, right? So this equation is the one we use to find the allowed wave functions and the allowed energies of particle in a fixed potential. Okay, it's like this. Imagine that we are still learning, we are still using the Bohr atomic model. So the Bohr atomic model, we have the center of the atom, which is proton and neutron. And the outer one, we have electrons orbiting the nucleus. And this electron, if it has different energy state, let's say this is the ground state energy, ground state energy. So if this electron is absorbing more and more energy, the orbit becomes larger and larger and larger. I don't know if you could see my hand gesture. Let me try. Sebab dia jadi, dia jadi apa? Jadi invisible kan? So the electron is moving in ground state. If this electron absorbing much higher energy, the orbit becomes larger and larger. So we have, see, the orbit becomes larger. So if we are still learning, if we are still using the atomic Bohr model, it is like that. But in quantum mechanics, we don't use the Bohr atomic model anymore. The electron doesn't move in the orbit just like that. So instead, the orbit now looks like a wave function, or it moves randomly. So different position, the electron with different energy, they will occupy different location of the chemical structure. They will be situated differently, not moving like an orbit, but they will exist at different place, which we cannot predict by the movement of circular motion. Instead, they will follow the quantum mechanics. Right? So, in other words, it tells us also which states are physically acceptable. Which physical states? N equals to 0, N equals to 1, 2, 3, or 4. Depends. It follows the TISE. This is where quantization becomes clear. Quantization means the electron can be quantified. The energy of the electron can be quantified. This is what quantization means. The energy level can be calculated clearly, just like the slide that I'm showing right now. So this is E equals to 1, the ground state. The energy level can be calculated. This is E equals to 2, N equals to 3, so on and so forth. We have so many. E equals to 1, ground state, E equals to 2, excited state level 1, excited level 2, excited state level 3, 4, and 5, so on and so forth, until the electron is being ejected from the atom if it receives energy much higher. Macam tu. So the energy level of the electron can be quantified. So the quantization is very clear. So not every energy is allowed in the bound system. Only certain energy. Not even in between E1 and E2. No energy is allowed over here. So it really quantized. E2 kat sini, E1 kat sini, there will be no intermediate state. There will be intermediate state, but it's not stable, so it cannot last. Okay, only E1, E2, E3, so on and so forth. That is why the TISC is so central. It explains why quantum systems have levels instead of continuous range of possibilities. So, in other words, quantization means the energy level is very clear. We could differentiate between energy levels, not a continuous or what is another word? Continuous or band-like system. Later in our discussion, I will tell you what does it mean by quantization and quantized energy level. What does it mean by band-like energy levels? Remind me, I will explain to you in the class. So next part, okay, this is a particle infinite well. So this slide shows one of the most important model in quantum mechanics, the particle in an infinite well. Infinite well, particle in between. The result is simple but powerful. The particle cannot have arbitrary energies. The energies are quantized. Arbitrary means it cannot have any energy. It must have specific energy. Particle in infinite well, to be able to exist in between the infinite well, they must have specific energy. It's a concept of electron with specific energy at the orbit of atom. Okay, so the energies are quantized, and the wave functions have specific shapes with specific numbers of nodes. Remember the concept of nodes? Group number 5, remember? So if you use the visual or animation on this slide, notice two things. Tengok saya punya animation tu. Oh, tak ada animation, gambar saja. Malah patutnya animation ni. Nantilah saya try. Anyway, nantilah dekat selepasnya ada animation. Okay, as I mentioned, notice two things. First, the quantum number increases. The wave function develops more nodes. Group 5 dah tahu dah ni. Kan? Group 5. Quantum number n equals to 2. The nodes equals to 1. Quantum number equals to 3. The nodes equals to 2. Okay, now, second, the energy increases very quickly with the quantum number. Betul. Because we have the equation of energy kan. Ni. Quantized energy level tu kan. Ni. En. En equals to n square, pi square, h bar square divided by 2 ml square. The energy level can be calculated using this formula. The formula will be given, certain parameters will be given. Definitely you can calculate the energy level of the electron. So what else? This model is useful because it gives us a clean example of quantum confinement. What does it mean by quantum confinement, sir? Tak ada quantization, ada itu, ada ni. Now, one more jargon, quantum confinement. So quantum confinement is like this. The electron in bulk semiconductor. Let's say this room is a bulk semiconductor. I am the electron. I could freely move in any three-dimensional movement in X, Y, in Z axis. I can move left, right, up and down, front and back and forth freely. Okay, now, this is zero quantum confinement because the electron can move freely. Now, if you ever heard the terms of nanosheet, what does it mean by nanosheet? Nanosheet is when we scale down, we make the bulk material size become smaller. Let's say we try to scale down the y-axis. Okay, tadi bilik ni 3 dimensi kan, kita rendahkan ceiling. We scale down the axis, the y-axis, scale down until become very small. I cannot move freely, kan? Because I'm trapped. The ceiling now has been scaled down. I only can move front and back, left or right, up and down tak boleh dah. So this is one-dimensional confinement. Now the electron cannot move freely. It only can move left, right, front and back. This is what happened in nanosheet materials. The electron is no longer can move very freely. It only can move to the sideways and front and back. Now, one more term. If you ever heard the term of nanowires. Nanowires. Ya. Nak terkeluar balik ni dekat Google Meet saya. Okay, so if you ever heard the term nanowires, so now tadi kita rendahkan ceiling become nanosheet kan? Now, how about that side of the room becomes even smaller? And now, I'm in this room, I have been trapped two-dimensionally. Ceiling rendah, dinding sebelah sana, apit ke sini. I only can move but very hard to the front and back and forth. Very limited, very hard to move kan? You kena himpit atas bawah dengan kiri kanan. Boleh bergerak ke depan ke belakang saja. Now, this is two-dimensional confinement. This is how the movement of electron happens in nanowires. Now, another term. Now, kita pendekkan pula dinding depan dan dinding belakang. Becomes even smaller and smaller and smaller. Now, this is what we call a three-dimensional confinement. Your electron is being confined three-dimensionally. It cannot move freely left, right, up and down, front and back. Cannot move freely. So what will happen if the electron is confined three-dimensionally? I will let you know during the lecture or during the discussions in Friday. Yeah? Try to have a think first. What will happen to the electron if we confine them three-dimensionally? So this later, the quantum confinement later will connect to real materials such as quantum wells, nanostructures, quantum dots, nanowires, nanosheets, so on and so forth. It's very important for you. So let us try to do practice number one, the normalization and probability. So at this point, I want you to treat normalization as more than a mathematical condition. It is actually what makes probability meaningful. In these problems, the aim is to check whether a wave function makes physical sense and whether the total probability equals to 1. So when you solve them, keep asking yourself what the answer means physically. If the function cannot be normalized, then it cannot represent any physically acceptable bound state. It must be normalized. It must be equals to 1. Then will be meaningful. So the purpose of this exercise is to make probability interpretation feel concrete rather than just symbolic. Okay. Look at the inlet. These problems, you can use AI. I don't mind. Try to use AI so that it will develop your understanding. I know it will be quite challenging for you, but try to use AI and keep on asking yourself what the solution gives us actually. Kan? Nanti I will ask you. I will ask you during Friday as well. Kan? Try to solve these equations. The normalization constant itu dah ada dah. Try to have a feel. How does the calculation is being made by the computer? Actually, problem number 2, problem number 3, the calculation is made by the computer. But try to use your own technique. You try to use your brain and hands. Try to derive how hard it is, how long of the time it will take to execute your calculations. Nak ambil feeling saja berapa lama untuk disiapkan kan. Right. Now we also have practice number 2. Okay, practice number 2. These problems pula, practice number 2 these problems are meant to test your understanding of what the TDSE actually does. I'm not interested in long calculations just as you are, and I'm more interested in interpretation. If a function is proposed as a solution, ask whether it behaves like a physically reasonable quantum wave. And ask what part of the equation represents time evolution and what part represents kinetic behavior. And the other one, what part represents the effect of the potential, the U. So if you understood the simulations earlier, this slide would feel more intuitive because you have already seen what time evolutions and barrier interaction look like. Try to challenge yourself. You can use definitely you can use AI. I don't mind. Right? So what else? Practice set number 3. These problems bring us back to the time-independent equation, the TISE, and the bound states. So the goal here is to connect the equation to allowed energies. The quantized energy levels. Maybe you need to calculate the energy level, kan? Okay. so the acceptable boundary conditions, and the shape of the eigenfunctions. What is eigenfunction? Saya lupa nak tanya. What is eigenfunction? The shape of eigenfunction. To calculate the energies, okay? And you need to know the shape of eigenfunction. What is eigenfunction? Oh my God. So when you work on these equations, always think in terms of physical restrictions. Why must the wave function satisfy the boundaries? Why do certain energies survive? Why do higher states have more structure? Kan, higher state n equals 1, 2, 3, 4, 5. Kita punya structure makin complicated kan. So these are the ideas I want you to carry forward, especially when we later study electrons in solids and energy bands, chapter 4, 5, 6, and 7. Cubalah challenge yourself. I know it's hard. You can use AI. I don't mind. Use AI. So as a summary, it's 6 already. Let me close the chapter by bringing the story together. We started with a wave function as basic quantum description of particle. We have psi, group 1, group 2. Group 1. When they introduce, we then introduce the time-dependent Schrodinger equation, TDSE, to describe how that state evolves, how the wave function evolves with time. So after that, we moved to the TISC, which helps us to find stationary states and quantized energies. Along the way, the simulations are not just for decorations. The simulation, the wave function, they are not the decorations. Later, we will look at it three-dimensionally. You see that, no wonder we are simulating this. Now we can see the electron's position. Later you will see that. So along the way, the simulations were not just not just decoration. It has some meaning. They were there to show you what the equations mean. Oh, nak terkeluar lagi kita punya Google Meet. What happened to Google Meet lah? So the tunneling simulation showed the transmission can occur even when classical physics say it should not. The wave and curvature visualizations showed how the mathematical form relates to physical behavior. Remember what curvature means to us. The particle in the box model showed how confinement leads naturally to quantized states. And if you remember those 3 ideas, then you already have the core of this chapter. So I think that is all for chapter 2. We will discuss further on chapter 3. Chapter 3, a little bit higher version of Schrodinger equation. So that's all for today, class. So thank you for listening and watching the simulation. So class dismissed.